Hello everyone, my name is Hailiang Zhu. I'm a computer science student from Shanghai Tech University. Today, I'm going to talk about my RIS project, which is about extending the detector's label space using pseudo-labeling. The project is under the supervision of Christoph Merz. The background for the project is that in autonomous driving, perception is crucial, and instance segmentation models are vital for precise object localization and identification. For autonomous vehicles, extracting the road structures, such as the lane markings, especially for navigation through the construction zone areas, is very important. So for our motivation for the project, it is that our lab has created an in-house collected robotics dataset, and the dataset is solely composed of images and annotations, focusing on objects commonly found in construction zone areas. Without ladder data, we cannot detect the road structures easily, and also the effectiveness of instance segmentation model is often limited to the label space of the dataset that the model is trained on. So that motivates us to incorporate extra categories into the original label space of the robotics dataset. And we start with adding lane markings by using pseudo-labeling, an approach helpful for generalize the model in new data domains, and it eases the process for labeling new instances. We use pseudo-labeling and use the two datasets here, which are robotics dataset and mapular vistas dataset. The goal of our project is to extend the label space of the original instance segmentation model, enabling it to detect lane markings. And this project also aims to contribute to a broader research area of training unified detector on multiple datasets. We can start introducing our method by mentioning the two datasets we are using. The robotics dataset is composed of more than 5,000 images and has 29 categories with the distribution shown below. It is an object solely about objects in construction zone areas. For the mapular vistas dataset, it is a street scene dataset with more than 100 categories. It is labeled panoptically, and lane marking general is labeled as stuff in the dataset, meaning we can extract the semantic information of lane marking and process on it. So let's introduce the pipeline of the method. First, we train specific datasets, detectors on both datasets. We run inference on images from the robotics dataset using the model trained on the mapular vistas dataset, which we can detect the lane markings. We then add pseudo labels to the original images from the robotics dataset. With the pseudo label dataset, we fine-tune on that and get a detector that also detects lane markings now. Here is an example of pseudo-labeling an image from the robotics dataset. We first run inference with the model trained on the mapular vistas dataset and get a panoptic result. We then extract the mask for lane markings and separate the mask into different instances according to the connectivity. We then add each instance to the original picture and form a pseudo-label image. Here is the result of our new detector. Although the average performance wasn't that good, but we can observe that the detector is doing a much better work on large lane markings. Since for the pseudo-label ground truths, we have a much larger confidence on large lane markings. This may help for further perception of the lane marking, since we often detect in an ordered time series. Larger lane markings are more likely to be the lane markings that we want to detect for the overall navigation process. We further tested on 50 manually labeled test set, and the result is shown below, which is similar to what we get from the former slide. To show that how we classify the lane markings into small, medium, and large. We use a visualization picture you can show in the slide. Here, for the qualitative example result, we can see that the large lane markings are often detected, and the new detectors often encounter false negatives for small and distant lane markings. False positives occur when no lane marking objects, such as the sound beams on the right, are incorrectly identified as lane markings due to their similarity. For the conclusions and future work of the project, we demonstrate that utilizing the approach of pseudo-labeling helps extend the label space of the detector, and the new detector is now capable of detecting lane markings. The future works include introducing new categories about row structures to our label space, and solve the conflicts when introducing new labels to the original label space. And how do we actually extract the lane markings for further perception for the row structures? This is all about my project. Thanks for your listening.